Hello, my name is Marco Riani.
And my name is a.c.atkinson. In this video, it is our intention to give an analysis of some data on the miles per gallon of a variety of cars.
These data belong to exercise 10.4.
We give a reference to the internet where the data can be found. The dataset has 398 rows and 9 columns and provides mileage, horsepower, model year, and further technical specifications for the cars. The number of rows without missing values is 392. So this is a sufficiently high proportion of the rows for us not to have to worry about missing values. The website from which these data were taken says that this dataset is recommended for learning and practicing your skills in exploratory data analysis, data visualization, and regression modeling techniques. To this, of course, we would like to add the use of robustness.
The goal of this dataset is to predict MPG, miles per gallon, using these 7 explanatory variables.
As is both customary and sensible, we start with an YX plot of all the data. These data are not, perhaps, of the greatest modernity. The origin of the cars are 1 American, 2 European, and 3 Japanese. There are no Chinese cars mentioned. It also should be made clear that these are internal combustion engines. There are no, for example, hybrid cars included in the data. Most of the explanatory variables in this dataset are continuous. Cylinders, number of cylinders, is an ordinal variable. However, origin is a factor. The labels 1, 2, and 3 that are given in the plot are entirely arbitrary.
We can see that there is an inverse relationship between MPG and the number of cylinders. This is expected. Then there is a nonlinear relationship with other explanatory variables. Finally, a positive relationship with model year. Of course, as the year increases, it is expected that the car becomes more and more efficient, and therefore the number of miles per gallon increases.
A slightly surprising feature is the relationship with acceleration. It seems that the quicker, the more powerful the acceleration for the car, the greater is the MPG. This is somehow counterintuitive.
The relationship indeed seems non-linear, non-monotonic, if you want. We start showing a fit in the original scale, which is our table A22. The value of adjusted R-square is above 80%. Note that not all variables are significant.
And indeed, acceleration is one of the least significant.
Finally, as concerns origin, there is a level which is significant and the other one which is not. Now we check whether the data have to be transformed. Given that y is just positive, this makes very much sense. Figure 8.76 shows the fan plot. The message from this figure is very clear. The trajectory for lambda is equal to minus 0.5 is always inside the bands. Actually, maybe when the last units enter the search, it approaches the upper bands, but the trajectory is always inside. Finally, as concerns all the other values of lambda, they are firmly rejected, and also the log transformation is rejected starting from n divided by 2. Now, from the fan plot, we want to automatically extract the information about the best value of the transformation parameter. So we run our automatic procedure, and as you can see that minus 0.5 is the best value of the transformation parameter. This is suggested both by the BIC and by the agreement index.
It is also suggested by the fact that for 0 and higher values of lambda, many outliers are found and rejected, giving to these very small values of the red boxes at the bottom of the plot.
Starting from lambda is equal to 0. Given that in this example the value of the transformation parameter was very clear, so we transform the data and now we do variable selection. This is the MATLAB output for variable selection. However, we checked that the R variable selection gives the same results, and these are the variables that are significant after the variable selection. So we have horsepower, weight, model year, and origin. Note that now both levels of origin are significant. The R square has increased and is now a bit smaller than 0.9.
In figure A78, we give a y-x plot of the transformed data for the significant explanatory variables. Note that we have transformed miles per gallon to the minus 0.5, so that the large has become the small. We're interested in thinking about our transform response on the scale of the original variables, although transformed. So we use minus the reciprocal square root of the data as our response. You can see that as a result of this, in the y-x plot, there is a very strong relationship between our response and horsepower, and it does decrease sharply. Similarly, as you would expect with the weight of the vehicle. The reverse is true, as we have already discussed, for model year. More modern cars are made to be more fuel efficient. There is also significance in the origin of the cars.
In the transformed space, we check the monitoring of residuals, and you can see that in this space the trajectory are stable. You may notice a slight decrease of certain residuals in the final part, and it is interesting to see what happens when we brush the units with the largest residuals. The brushed units correspond to a particular region of the space, which is very evident in the scatter of transform response with weight, and these units are characterized by values of model year that are among the greatest. Now we can do a brushing in the lower part in order to see the position of the largest negative residuals. Also, the largest negative residuals lie in a particular portion of the space. For example, it is interesting to see that in the scatter of transformed response with weight, these units with largest residuals have values which is generally below the main bulk of the data.
So these vehicles have an MPG which is less than would be expected for their weight.
The analysis so far has been parametric. Now we move to the non-parametric analysis. So we run the automatic model selection procedure based on REVAS in order to understand which options have to be used. The automatic procedure shows that we have just two solutions which have a p-value of the both Darwin-Watson test for autocorrelation and a p-value of the JARC-BER test for normality which is in both cases greater than 0.05. These two solutions, as the right-hand panel shows, have a correlation which is 0.997. Therefore, they are virtually indistinguishable. Figure 8.22 shows the output of the best solution. Some outliers are found, and they are especially visible in the plot of transformed response against fitted values.
We can see, however, that compared with the outliers or influential looking observations that we were finding when we were using linear least squares based robust methods, we have found here very few outliers.
Finally, as concerns the plot of transformed x against x, we notice that there is a monotonic relationship apart from acceleration. And in fact, if you remember, when we commented the initial relationship between y and acceleration, it seemed that this variable had a sort of S behavior. So that indicated a non-monotonic behavior between acceleration and miles per gallon.
We would particularly like for a moment to dwell on the top left-hand panel, that is the transformed response against the untransformed. In many of the examples that we have seen or that are in the book, the response can be well approximated by some kind of power transformation of the Box-Cox type. However, here we have a non-parametric transformation that is clearly curved to begin with and then straightens out in a way that the Box-Cox transformation, if appropriate, would not do.
So after excluding the outliers, and this is the ANOVA table in the transformed space, we end up with an R square which is 0.91. We end up with a model in which all the variables are highly significant. Therefore, in this case, the non-parametric analysis seems to capture features in the data that cannot be taken into account by the parametric analysis. Now, these variables are all significant, and we want to have further information about their significance, monitoring the added variable T statistics.
We just want to confirm to ourselves that the information for these transformations is spread throughout the data, that it doesn't come from some quirk of outliers towards the end of the search. So the most significant variable is x6, which is the model year. As the model year gets greater, as the cars become more modern, so the fuel economy improves.
And note that there is a steady increase, a steady departure along the search. So as more observations you include, then the more this variable becomes significant. And the same is true also for X4.
X4 is body weight, and this must be highly correlated with the year of manufacture, as manufacturers were concentrating in this period on making lighter and more fuel-efficient cars, and it seems that their efforts have been satisfactory, or successful, let us say.
Finally, as concerns X2, X5, X1 and X3, you can see that they are significant, and maybe the only X2 is the only one which becomes significant just in the final 20-30 steps of the search. And as a final thing, notice that we have given in red the step in which the outliers detected by REVAS enter these different forward searches. And then you can see that these outliers generally enter the final steps of the forward search.
And although they have some effect on the significance of the t-statistics in all cases except x5, it is not out of line with what has been happening from the addition of non-outlying observations.
In the final plot, we give a scatter of the transformed response against model year and weight. This is a 3D plot with the outliers in red that have been found. Of course, the 3D plot depends on the angle of view, and in this angle it is not clear whether these outliers lie in a particular portion of the space. But if we now rotate this data, you can see that the outliers indeed lie in the two different sides of the regression hyperplane. And in the transformed space, look at the nice regression plane that has been found by the non-parametric transformation.
A summary of the importance of this plot is that after appropriate rotation, the outliers lie far from the bulk of the data. There is a clear reason why they have been recognized as outlying. An interesting feature of the analysis of these data is that in many countries it is not miles per gallon or the metric equivalent there, but the amount of fuel used per 100 kilometers, fuel presumably being measured in liters. So this is the reciprocal of the response with which we have started. It seems from the slight difficulty interpreting the result of a transformation with lambda equal to minus 0.5 that the metric measure of performance and efficiency might be more suitable.
This is the end of the analysis of this dataset. Please let us know in the comments to the video if you have queries and or you'd like some further analysis. Thank you for watching, and we look forward to having your feedback.
Thank you very much, and arrivederci.